Is Cooper Stone, and this is my Physics 2212 Lab 5 about Faraday's Law. So the purpose of this lab is to both experimentally and computationally determine how an induced current caused by a falling magnet acts against its movement due to Lenz's law. So in other words, the time the magnet takes to fall through the tube will be determined experimentally and computationally before being compared. And in this case, we assume that air resistance is negligible and that the net force on the magnet is exactly equal to the sum of the magnetic and gravitational forces. And the main results were that the experimental time to fall was 1.56 seconds. The computational time to fall using the Lab 3 magnetic dipole was 2.412 seconds. And by adjusting this dipole moment to 1.888 ampere squared, we found that the time matched that of the experimental data. Some basic essential concepts include Faraday's law, which says that the integral of the electric field and path is equal to the negative rate of change of magnetic flux. And in this case, we'll be using the formula at the bottom of this slide to determine change in magnetic flux, as opposed to the formula shown above with the integral of magnetic field and hat and area. Additionally, we will be finding magnetic force by saying equal to the cross product of current and length, or path length, times magnetic field. And we'll also be using Ohm's law to determine the relative amount of current induced in the foil by saying it equal to the induced voltage, or the rate of change of the magnetic flux, divided by resistance, which was a preset value. So for the experiment, it just involved gathering a bar magnet or aluminum foil, measuring the dimensions of the aluminum foil, and timing it as we dropped it through the tape, the foil. The computational method involved modeling such a tube and magnet, setting the relative magnetic dipole moment, and then finding the forces of gravity and the magnetic force induced by its movement, and then determining how long it would take to move all the way through the tube. Here's a relatively simple diagram of the experiment. As you can see, as the bar magnet moves down, in this case, the magnetic flux is increasing downwards. So to act against it, according to Lenz's law, which states that nature abhors a change in flux, a counterclockwise current, as seen from above, will be induced in the ring to create an opposing flux moving upwards. And here you can see some of the basic experimental results, such as the basic dimensions of the tube, the mass of the magnet, and then the amount of time it took for it to fall all the way through the tube, and then the magnetic dipole moment determined in Lab 3. And here you can see some of the basic parts of my glow script code, such as the dimensions of the tube, basic constants, mass, things like that. And then you can see the function I put there to generate the magnetic field of the bar magnet. And then a similar function can be seen here, which found the rate of change of magnetic flux due to the falling magnet. And then this was combined with the 3D modeling to create the overall simulation of the bar magnet falling through the tube. And here you can see a screenshot of the simulation as it falls through the tube, with the blue and red rings demonstrating the induced currents created by the falling bar magnet. And here are the results with the magnetic dipole moment from Lab 3 on the right, achieving about a time of around 2.5 seconds, and then the adjusted magnetic dipole moment of 1.5 seconds. So obviously the experimental time was less than the predicted time, and assuming that the experimental design was correct and the computational code was all correct, this suggests that the previously measured dipole moment was larger than the actual dipole moment of the magnet, because reducing it to 1.888 amperes squared resulted in a much more accurate time. And some sources of error in this lab could have included air resistance, human error in timing the magnet's movement, and then measurement error for finding the dimensions of the tube. The coloring on the tube indicates the different induced currents, with blue being counterclockwise and red clockwise to oppose the change in flux. If you flip the magnet around, a similar result happens, however, the poles are different, but the same currents will be induced. And then I previously discussed the comparison between the real-world system and the computational system. And then the shape of the plot tells me that after they reach steady state, the forces of gravity and induced flux are equal in magnitude, but opposite in direction. The resistivity of the conductor was reduced as close as possible to 0. Then the current would increase, which would extend the time the magnet takes to fall. And if holes or slots would cut into the tube, it would cause fewer closed rings around the magnetic field, lowering the induced current and decreasing the time the magnet takes to fall.